Okay, so I am going to do a quick review. Would like to go through some math problems that may and or may not be on the exam. Just a quick refresher. Um, take into heart what some of the feedback you guys said. I really liked what you brought to my attention for me to improve and make things better for you. So I thought let's go back through some of the old labs and worksheets that we have done earlier in the semester and just kind of freshen up on this sort of stuff. So the exam, what I have after this class, I'll get the exam posted. It's I'm kind of using an older test that's been used for this class in past semesters. So it's going to be one of those print it out, fill it out, scan it back in, resubmit it kind of deals. Um, it will be live. Give me a little bit of time. I'll say by like noon today. As soon as I can get this video processed and online as well. So give me a little bit of time after class here. Um, but I will give you till midnight Friday to get this completed and submitted. Does that sound good? So with that said, I don't have anything planned or any need for you guys to come in on Thursday for actual lab time, unless you guys want to come in and just hang out and talk surveying. You know, that'd be cool. I'm good with doing that. Otherwise, this will kind of be our last in-person meeting. I know I'm trying not to tear up with that kind of thought. Sad it's getting close to the end here.
You teach some of the higher level classes too, right? Are there any classes that we haven't taken yet that you still have to teach us?
This summer, I do the geospatial surveying control class. And then in the fall, photogrammetry, remote sensing. Those would be probably the only other two. And this summer, I've got to spend a lot of time getting that photogrammetry and remote sensing lab class kind of up to speed.
I got 3 classes with Jim in the fall. And then I bring my physics teachers in. But
Awesome.
man, I got no Chris.
No Chris.
Physics in person? Yes. I told her I was like, I can't do it online. I can't do any of the math. I can do algebra online because it's algebra. But like, I would not have wanted to do trig online. I would not want to do physics online.
Don't blame me at all. So I did take into consideration some of the feedback as far as like you guys wanted to be a little more engaged with some of these lectures and things. So I do have some various handouts for us to work through today. We can spend as much time as we want. I have 4 worksheets or worksheet packets for us to work through. You know what? Maybe I ought to just hand all of them out right now and we'll just call it good. Save me a little bit of time going around later. Let you guys kind of look at these and decide how much time do we want to spend on each. Let's see, is this one?
So did you get my email on that?
I did. Sorry, I have not replied, but I did see that. Yeah, it's this week has been a little extra busy, a little extra chaotic.
I don't know if you've made look at them yet, but the two.
I have not.
Well, two. I'm just gonna let you know. 2 of them I like lost the packets for, so I downloaded I downloaded the PDFs and then I edited it straight onto the PDF.
Okay.
So it's not like the packet that you gave me that I had originally, but the rest of them are all handwritten and like photo submitted.
Okay. I'm sure it will be okay, and I'm sure we can work through it. So this first packet I handed out, wouldn't mind working through here, is just touching on horizontal curves again. This first problem I have here, you got a little bit of curve information. Fill in the blanks of some missing pieces. So I've given you a radius I'm giving you a PI station. I'm giving you a forward and back bearing. What I would like for you to calculate from here is the delta angle, the interior angle of the curve, the length, the tangent, the chord bearing, and chord distance for this curve. Um, right off the bat, let's go ahead and start with the top one here, the delta or interior angle. Who wants to tell me how that can be calculated with the information provided? So how are we calculating the deflection angle with the information provided here? Yeah. What is the delta angle of the interior? I'm sorry?
You add the two, subtract 180, so you got a southeast bearing and a northeast bearing.
Yeah, essentially this right here, this angle is equal to your delta. So yeah, you have a northeast bearing, you have a southeast bearing. You can pull this southeast right down here, and if you think of this way, you draw yourself a little north line, north arrow. My southeast bearing is this angle here, my northeast bearing is this angle here, and what I'm solving for is this part right here. So that is correct. If you add the two and subtract that sum from 180, that would give you that angle.
Does this have BMS on it?
It should give you your answer in the BMS.
Oh, I see it. I see it. Got it.
So like,
Yeah, this one.
so like, so like, 70 degree, 50, just did the degrees up again. That,
So what do we? Anybody have anything? You got?
This one, it knows that that's.
yeah, no,
Okay. Okay. And
Oh my goodness! All right. Anybody got that delta angle yet?
25, 26, 44.
Excellent. Good, good, good. So another important piece of information you're going to need to calculate a lot of this stuff is going to be your half delta. I don't have an actual line for that. I'll just write this delta over 2. I would recommend finding that right away.
this is the best degree to net seconds.
That's why I bought it.
Is this that's legal?
Yeah,
I have to get this one.
it's the same calculator I sent you in the
Your jacket.
Yeah.
I love the TIAs for it. Great for like everything math, but it's pain to use degrees and seconds on that thing. It's literally like to do 1 degree, it's 3 button presses, and then
Right.
then 3, and then 3.
The Casio and the TI, they all do the same thing. I think the Casio really excels when you're doing math with angles, as far as ease and simplicity's sake. So does anybody remember like some of the equations we need to solve the rest of this stuff here? So
I know the delta equation if you have length and radius, but have you ever done delta? There's was it tangent times 1/2 or tangent times half theta equals length, or is it there's something else in there? Is it tangent of half theta times radius equals length?
your tangent length is equal to the tangent of your half delta times your radius. Remind me there, what's your length equation that you have there? If you have your length and delta and radius, you
Delta equals length times 180 over pi r. And there's a third one, like
Delta over 360 times 2 pi r is your length says. Now that's this flip chart I'm looking at. Unless it's, oh, that's your delta. You're saying delta.
so to do your length, that would be, got to do a little gymnastics to rework that one out. Okay, either way. Just some practice worksheets of things that may and or may not may probably be on the final exam. Yeah, these are most likely going to be types of problems you're going to deal with on the final exam. However, this is not the final exam problems, but very close to. What do you got for me, Jake? Have you calculated anything up yet?
No, because I was distracted.
Colin, what you got for me? So another thing to consider, so we're looking at this here with that dashed line going across is your chord. The angle from this tangent line to your chord, that angle is equal to your half delta.
Got a big negative number for my chord distance.
Your chord distance, is that also your, what they call your long chord?
Yes.
Yeah.
Yes.
I got 440.47 round. That may or may not be right.
So taking your half delta, which we calced already, the sine of that times 2 times your radius, given an answer of 440.47. Can anybody confirm or deny that? I don't know what this blackboard was or whiteboard was cleaned with, but man, it's not very erasable.
Is it's sine half delta is in times 2 radians?
Yes. Does it make more sense to put it like that?
How did you get it?
So,
I didn't even check for something, just put it in the calculator one time.
You helped us half delta. What was that? It was like 12.
12:43-ish.
I will also reiterate here as well, when giving answers of bearings and or angles, I would like to see those answers in degrees meant seconds, not decimal degrees. Let's make that seeable.
Which equation did you use to get the coordinates? You used that one? Yeah.
The sine of your half delta times 2 times the radius.
Would you get like 311?
I got negative 1300.
Here we go.
Thank you.
Going through math that of some types of problems you may have that may and or may not be on the final. So first things first, with that delta angle, we know the is the angle between these two tangent lines. We have bearings, so we can do the math.
Are you putting your current speed graph?
With the 2 rad. Yeah, I can do that first time.
Oh,
That was a drop.
I was reading that.
Oh yeah.
That'll do it.
Make sure you're not in radian mode on your calculator.
I was like, why am I getting such different answers?
I will confirm I do agree with that 440.47.
Yeah, that's fine.
Hey, John, how do I know if I'm in radian mode?
Go mode.
I'm borrowing this computer.
I've never messed with it, so
It was right. The number was right the first time, so.
it should be in degree mode. I've never messed with it. I think we just plugged in DMS and so it was in radian mode. I don't think DMS.
Well, nuts.
You find out, let me know.
Oh, I mean, if you look at the top of this thing, it says T. Like there's a bunch of different settings for that. Amazing.
So we start talking about, we're breaking everything down into triangles. The old SOHCAHTOA is all that we're really doing here. We're doing is taking that from the PI. If you were to draw an imaginary line up to the radius point. You're breaking this down into smaller triangles. So like for your chord, this angle is your half delta. This is your radius. We have essentially the hypotenuse of this triangle. We have the adjacent, we have the hypotenuse, we're trying to find the opposite side. This is what turns out to be actually 1/2 of your chord distance. That's why once we calculate what this side is, we multiply it by 2 to get the total. So if you run a line straight up to your PI, from your PI to your radius, we're looking at this triangle right here. This being 90 degrees. Your radius is your hypotenuse. We're going to find just this one opposite side, multiply it by 2, and we get the full thing. Yeah? Tangent is the same way. So we know that tangent length is the distance from the PI to the PC, or the PI to the PT. They should be equal. What you're more or less doing there is again, that triangle's split in half. The angle here is our half delta. Our radius is now, this is 90 degrees here. Our radius is now our adjacent side. We're looking for the opposite side. We have the adjacent, we have our angle, so that would be the TOA.
I'm getting a number bigger than 360 for like the degree of the arc. I guess we don't need that.
The what?
What's the chord, the other line above the chord on this side?
Your chord bearing.
Oh, okay, that's why I'm not calculating.
So we know if you project this tangent straight through, this bearing stays the same, moves down here. Knowing the bearing of this line, knowing the bearing of this line, we can calculate this interior angle. So if you were to draw an imaginary north-south line, you know your bearing is this portion down here. Your northeast bearing is the portion up here. If you add those two together, subtract that sum from 180, that'll give you the remaining little piece here, which is our delta.
L is arc length, right?
What?
L is arc length, the length of the curve.
L is arc length, yes.
Okay, that's what I meant.
That is the length along the arc. That should be a bigger distance than your chord distance. Your chord should always be shorter than your arc length.
But I'm getting it like a degree. Because isn't the equation is delta times pi r over 180?
So you're saying the L would equal,
That's just what I have written down. And if you redo the delta equation, that's what you get. Right?
so if I take my delta, That's what I'm getting for an arc length.
I got a degree. Like I got 444 degrees, 6 minutes, 31 seconds. That's weird. It is. Like you have to change it back to DMF. Like you get to.
No, it's a length, so it's not
Well,
in angles.
The equation.
So
Turning that in and turn it into a.
you punch this in, you multiply that by pi, and then you multiply it by your radius, and then divide that whole total by 180 degrees. Or I'm sorry, just 180. And you're coming up with a degrees minutes seconds?
Yes.
Huh.
I've never used this calculator.
I was gonna say it sounds like a calculator type
Maybe
thing.
I have to divide it by 180 degrees, so it cancels out the degrees. But I don't think this calculator knows that.
You're asking me how to work a calculator that I don't know how to work there.
I just got weird.
Does anybody agree with that arc length? Okay. Got 3 more pieces of information to solve for.
Did you solve for your cord bearing yet?
Not yet. How are you solving for that?
I took 7450 47 and I added on your net delta.
Yeah.
I got 8734 right now. Be a southeast bearing.
South, would you say 87?
3409. I'll try to check this up here.
So you said you take the two, and we already know, add those together, and just subtract them from 180.
To get your delta, your full whole delta, the full whole interior angle of that.
How do you get the cord?
So, Gavin, future heads up. When you use this thing, if you're using these equations, when you do that divide by 180, or probably when you do that multiply by 180.
What if you took that?
You gotta add the degree symbol. I added the degree symbol and I divided it.
What if you take that degrees, minutes, seconds, convert that into decimal degrees, and then multiply and do your division?
I don't know how to do that. I don't know where the DMS button is on this thing. I don't even know. Yeah.
Yeah, those are really good.
No, it is typing in the actual.
Doing some angle math is very simple in there. However, I don't know fully how that all works. So
This thing has potential. I know. I just have to master it.
the TI and the Casio do the same things. It's all kind of what you're used to, what you're familiar with.
I just had to put the unit on that 180, and it canceled out the degrees.
Oh, made that 180 degrees.
Yeah, when I divided it, and then it gave me what I needed.
Okay.
I guess this would be the decimal. Well, not really. Because did you get 444.108 when you round up?
Yeah. When we do distances, just give it to us in the nearest hundredth of a foot. Okay, how about the PC and PT stations? How are you going to calculate those? One more time, a little louder. Big surveyor voice for me. Your PI station minus your tangent, and that will give you your PC station, correct. So if I got a PI station of 12 plus 47.65, subtract your tangent length of 225.78, and what's the PC station you came up with? Yeah. All right. How do you get your PT station? No. to get your PT station, you have to take your PC station, add your arc length. So if we remember from stationing, that is distances along, like when we're talking about roadways, along the alignment. So that's going to be along the center line. How long is the curve? That would be the arc length. So add your PC station to your arc length, and that will give you your PT station. Yeah. Questions, comments, concerns? So overall, does this feel like a section like you might need to revisit the labs and the lectures to kind of help fortify this a little bit more? So if you're given a problem similar to this, you got your two bearings, your forward tangent, back tangent bearings, you can do the math of those bearings to get this interior angle, which will equal the delta, or the whole entire interior angle of the curve. The angle from your tangent line to the chord is equal to your half delta. So once you get that full delta, it's real good to, find out what's your half delta right away. Plus, you're going to need that when you do your find your tangent and your chord lengths.
So why, if you subtract your PI from the tangent, how does that give you your PC if it's not a straight line and the stationing is along the alignment, right?
Because I said so. That's just the way it is. If you have a PI station, you need to calculate this tangent, and that's just how you get back to it. I mean, we're not going to calculate like half of an arc length, and that's going to be a lot more math to work it that way. This is just what's generally done, accepted, is take your tangent length, go back, and then to get your forward, your PT station, point of tangency, the end of the curve, you need to add the arc length to get your PT station.
You would hit in the spot, but then I just wonder, like, if you get a really long curve or something, I wonder
If you took your
if that would actually take off.
1247.65,
If it don't.
if I added the tangent length to the PT, or sorry, the PI, I would come up with a station of 14 plus 73.43. So that's off quite a bit. And again, stationing is
That's
along the element. In this case, it'd be along the arc length. So go back, get your PC, and then go forward along that element to get your PT. Good? Oh boy, I don't know if I can do this here. Have enough space. So if you're given a chord, or I'm sorry, curve information for math. Okay. Am I doing that bad with what I'm writing down so far? No, no, just I can only zoom in and out on that screen for this. But thank you. I think I'll be okay. I hope. calculating deflection angles running through here. We don't have to work through every single one of these, but I'd like to work through a couple of them. When calculating your deflection angles, we're essentially saying we have our instrument set up at our PC. We are going to backcite this tangent, which would take us to the PI, and say that's 0. So what angle do we turn to get to each individual station, as long as what is the distance from the PC to each station? Oh, darn it, I don't have that written down there correctly. The long, this should be like the long chord, and maybe I should have another for your short chord. The long chord is the straight line distance from the PC to whatever station you're going to. Your short chord would be the distance between some station interval. So if you're going every half station, which would be every 50 feet, what would be the short chord? What's the distance between those 50-foot stations? The chord distance. Does that make sense? Clear as mud? So what we really need to do here is we got to break this entire triangle or our entire horizontal curve into smaller pieces. Say I want to go to 14 plus 0, 0. I want to look at this smaller portion right here. I know my PC station and I know what station I'm going to, 14 plus 0, 0. So that would give me the arc length, correct? If I subtract those two stations. That's going to be critical. So if I went to 14 plus 0, 0, that's going to give me, and subtract the station I'm going to from the PC station. For example, right there. Yes? Confirm, deny? So now what we need then is we have our radius. We have an arc length. We need to find the delta. What is this little interior angle here? If we go back here, we know that that formula is, where can I write that somewhere? You can see it.
Length times 180 IR.
Yes.
What did you find out arc length again?
Subtract the stations. So whatever station you're going to minus the PC station, that is the arc length for this one segment. Yep, yep. Not a problem. That's what we're here for.
I knew it was simple. I was like trying to like think of an equation or something.
No, nothing too crazy here.
It's just that okay.
Now, I'm going to just kind of go back to this again. I want to reiterate this point. From your PC to your PT in this case, the angle from your tangent to that chord line is equal to your half delta. If you think of this way here for an example, our PC is station 12 plus 67, 39, and this would be 14 plus 0, 0, what we're going to. If this was just this segment, once we calculate our delta, we take our half delta, and that is our deflection angle.
Kevin, do you know why this thing doesn't give you decibels?
No, not really. We were just looking at it before class.
I mean, it gives it to you like as a fraction.
Yes, confirm, deny that deflection angle that I came up with. So I took my arc length, multiply it by 180, divide that by pi r, and that gave me the full delta. The half delta is your deflection angle, which you're going to need your half delta to find your chord length, long chord length, which we also said is chord is equal to the sine of your half delta times 2 radius. Yeah? Confirm, deny? And again, I also want to reiterate your chord distances are always going to be shorter than your arc length. Think of that the arc length is along the curve, and the chord is a straight shot from the beginning to the end. Yes. How did I get the the delta angle? So to find the interior angle for this little segment, I look at this equation right here because I want to solve for delta. I have the length, which is the arc length, times 180. Take that sum, that product, and then multiply pi r, pi times radius, and take that, divide those two products, and that will equal your delta angle. Yeah, questions, concerns? Are we feeling it?
Your deflection angle is not your delta angle.
It's your half delta.
Deflection is your half delta.
Correct. Deflection is your half delta, which again is convenient because we need the half delta to find the chord distance. The long chord being the distance from the PC to whatever station you're going to. Long chord is always from the PC to wherever you're going to along that curve. So for the fun of it here, if I look at, say, station 16 plus 0, 0, to find my arc length, I subtract my stations. 16 plus 0, minus my PC station of 1267.39 gives me an arc length of 332.61. So I'm going to go back into here to find the delta with this new arc length. So 332.61 times 180 divided by pi times your radius, pi times 800, will give you your delta angle. And once I have that delta angle, I want to divide that by 2, get my half delta. And I come up with a deflection angle Now I'm going to take that deflection angle, take the sine of that times 2 times my radius, 800, to get my long chord. Easy pizza cake, right? Is this making sense? Are people confuzzled?
And then your short core distance used to
So let's say between station 16 plus 00 and 15 plus 00, that would be your short chord, just in between these individuals. So what's your arc length between 15 plus 00 and 16 plus 00?
it's 100.
100. Throw that into this equation to get your delta, divide that by 2 to get your half delta, take the sine of that times 2 times your radius, and that's going to be your short chord.
For like this, filling out this,
Mm-hmm.
wouldn't your short core just always be 100?
That's the arc length.
Oh, shut up. Like, aren't you setting it the same? There you go.
Your short chord, whatever you calculate, is going to be the same between like 13 and 14, between 14 and 15. Your long chord and short chord from your PC to your first station is the same thing. Now, between your PT and your last station, that's going to be the short chord. What's the difference there? Your long chord would be your PC to PT.
Okay. I get it. Long chord always goes back to PC.
Correct. Long chord always goes back to the PC.
Short chord can be whatever you want.
Short chord is going to be between whatever these intervals are that you're looking for, as well as the last station and the PT. So that would be a different short chord as well. We feeling good about this?
I just need to get the formula down for this one. This is the metric from last time.
Not a lot of crazy formulas here. Feel free to look over. I'll get this lecture video posted this afternoon. So how are we feeling? I don't want to spend too much time doing this because I got a couple other things I'd like to run through with you guys to do some more calculating. All right, I'm gonna do a super easy one here real quick. How about the PT? What's our deflection? What's our arc length, deflection angle, and long chord? Come on, that one should be like a no-brainer. I know it's going to take an awful long time. What's my arc length of the total overall curve? My deflection angle is just the half delta. So if I take my delta angle that I have up here, 54 degrees, 33 minutes, 32 seconds, divide that by 2. And what's my chord distance? Boom, that's an easy one. And again, I just would like to also reiterate here, if you notice the ones that we have done, the chord distances are shorter than your arc length. So if you guys want to keep practicing through that, great. I would like to move over to another sheet just to work through that real quick. If we have any more time at the end, or if you got any more questions, please holler at me.
Is this? I know you said that because you made the midterm exam, right? That was your test.
That might have been part of like an old thing, kind of like this here.
And like, is this exam?
I might have.
Is this exam gonna be similar to how the midterm exam was set up?
More.
I remember that it was like 5. It was pretty much this packet. Similar to this packet. It was like 5 questions like that.
Yeah, yeah. Yeah, the packets, the final's going to be stuff similar to this. And I just want to kind of rework through this just to help refresh all that. How about we look at, I think this would be a good, important one to look through as well. Oh my. Maybe we'll jump back. Yeah. You know what? Hold on. Last page on that.
I bet there's a mode that you can change in here. I couldn't find it, but
I got the paper stuff for it at home.
I don't know what the S stands for. I would assume the D stands for decimal.
Let's just look at this real quickly. There may be an instance where you need to solve something here. And I know I said earlier in the semester, the only time you're ever going to have to calculate these is in this class. Well, for future reference, you may have to calculate some more of these in route surveying class. So let's go over this just one more time for the fun of it. I'm not going to calculate all of these, but I want to touch on a couple equations really quickly. So we recall to solve for a vertical curve, we're using the quadratic equation. Come on, pencil, stay with me. Tell you what, there's nothing worse than when you drop a mechanical pencil and then all the pieces of lead inside break. Oh, come on. Y equals a x squared plus bx plus c. Nice and easy equation. Nothing too terribly hard, nothing too terribly complex. Y is the elevation you're solving for. A is equal to the rate of change divided by 2. I'm not doing this very well. B is equal to G sub 1. C is equal to the beginning vertical curve elevation, BVC elevation. X is the horizontal distance from the beginning of the vertical curve to whatever station you're going to. One of the first things we need to calculate for this is R, because we're going to need that for what A stands for. R is equal to G sub 2 minus G sub 1 divided by L. G sub 2 is your grade out. G sub 1 is your grade in. And L is the total horizontal distance of the vertical curve.
What does BVC stand for?
I'm sorry?
What does BVC stand for?
Begin vertical curve elevation. So you have a BVCS, a BVCE. BVCS would be begin vertical curve station. BVCE, begin vertical curve elevation. So if we were to calculate this, here's the way I do this here. I would take my grades, which are in percent, and I would convert those to the decimal, divide them by 100 to get them like decimal form to do the actual math here. So negative 0.04 minus positive 0.04 divided by 700 would equal my R.
G1 is your plus 4%, G2 is your minus 4%.
Correct.
So is G2 always supposed to be the -1? Well, I guess that doesn't necessarily
No,
matter.
just in this case, it is. This is a crest curve.
But you could have like a go up.
Yeah, if this was a sag curve, your G sub 1 would be negative, your G sub 2 could be positive. It all depends on what type of curve you're dealing with. In this example that we worked through before, I think in class, this is the one we had. So these are pretty much the main things that we need to look at, focus on, and deal with first off. Well, kind of. We need to find the BVC elevation. We need to find a BVC station so we can find a BVC elevation. Can we do that much? The PVI station 50 plus 0, and the elevation of that is 789.30. This is going to play into one of the next things I want to look at after this. This is kind of more simple and might fall along the lines of like what you were thinking with that horizontal curve, finding your stations. You have a PI station. To get to your BVC and your EVC stations, you're just going to divide your total length by 2. So half of 700 minus your PVI station will give you your BVC station.
Why half a second?
Why not?
Because there's no. I'm looking at our equations. There's no like.
Because I said so.
Is it because you're at the halfway point?
Yeah, your PVI's halfway, so we'll take half of our 700 to get back to this.
And you guys point of vertical.
PVI,
Yeah.
point of vertical intersection.
Intersection.
So, like a horizontal curve where you have a forward tangent and a back tangent, if you were to extend those, where would they meet? We're just looking at that now from a horizontal curve is kind of like looking from a plane down. The vertical, we're looking from like a profile view, but similar concept there. So my BVC station, I'm coming up with 46 plus 50. Yeah. Okay. Half of 700, half of my length is 350, right? Think of the old rise over run equals slope. Remember that equation I've gone over a few times? We know our run, we know our slope. Our run is this portion here. We have the slope. We can calculate what the rise would be. And in this case, because we're going down, we'd subtract that from our PVI elevation to get our BVCE elevation. Yep. No? So we need to solve for rise. Confirm, deny? All right. So again, looking at this right here, I want to solve for the rise. I know my run. That's from the PVI station to the BVCE station, which is half of our length. We know our slope is 4%, so I calculated what the rise would be. What's the change in elevation between those two? And because I'm going down from the PVI, I subtracted that and come up with 775.30. Yeah? Since we have the same grade in and the same grade out, your elevation is going to be the same at your EVC, your end of vertical curve. Your station would just be taking that 50 plus your 370, 350, or the total arc length plus your station. You're going to get the same number that way. So real quick, let's calculate what's our R value. So if I take a negative 0.04%, and subtract 0.04. Divide that by the total arc length of 700. I come up with an R value of negative 0.000114, something like that. Now we have our R and we have our BVCE. This is easy to solve for any station. X is going to be whatever station you want to go to minus your BVCE. That's just that horizontal distance. That's going to be the same in this first portion here as it is the second portion of the quadratic. We solved for our R divided by 2 times your distance squared, plus B, which is G1 times your distance, plus C, which is your EVCE elevation.
Your arc length is not something that matters when you're calculating stuff. Like that length is just the horizontal length.
Correct. So there's just kind of down at the bottom there, reworking, putting all of this stuff into the quadratic. So the elevation you're solving for is equal to R divided by 2 times your distance squared. I would recommend do that little portion, then take G1 times your horizontal distance, do that little portion, then start adding those up. So if I wanted to go to that first station, for example, 47 plus 0, my horizontal distance would be 50 feet, right? That's going to be the X value for this first one. So just kind of, hopefully you can see that okay. I just roughly punched in all the numbers I have. So my R divided by 2, divided by 50 squared, add that to G1 times 50, and add that to your BVC elevation. Pizza cake. You got a confirmation on that?
Maybe.
Maybe. No angles involved in this one.
I found the. I did. I found the elevation for the other side. It's not the BBC on the other side. It's
The EVC?
BBC.
That should be the same as the BBC elevation then.
It's the exact same. That's how I knew it was something was wrong. So I thought I was doing the in between. I didn't use that 50-foot radius. I used the whole not the radius, the distance.
Yeah, so that 50
That's in between. That's from station to station to station.
is essentially the length from your whatever station you're going to your beginning of your vertical curve. All right, I want to throw another equation on you that I haven't thrown on you before. This may and or may not be probably important if this happens to probably occur on the final exam. I'm trying to be very subliminal here. You guys are picking up on what I'm putting down, right? What if I wanted to find where the high point or low point is of a vertical curve? In this case of a crest curve like this here, where's the high point? Where's the high point along the vertical curve? Is it? Maybe, maybe not. I'm going to say good chances in this scenario, probably, because you're same grade in and out. So to find that distance from the beginning of your vertical curve to wherever that high point may be, we need to solve for x. So for the high point or the low point, x is equal to negative g sub 1 divided by r. That will tell you the distance from the beginning to wherever that high point or low point may fall. We have our r, we know our g sub 1, so if you take that negative 0.04 divided by negative 0.000114, you get an x, a distance, a length. In this case, I get a distance of for a high point, an x of 350.88 feet. If I were to add that to my BVC station, I get a high point station of 50 plus 0.88. So yes, pretty darn close to being right in the middle. Station. BVC station. That's a distance. X is a distance.
Yeah.
So add that to the
Oh,
station
gotcha.
to find out what station that falls on.
Yes.
Then you could very easily take this X, plug this back into here, your quadratic, to find out what's the actual elevation of that high point. So if I take that down here, now I'm looking at this equation, except now where I have my 50 from the first one that we solved for, I'm using an X of 350.88.
Sure. Can you flip that a little bit?
I'm sorry?
Could you like hold it down a little bit?
Oh, sure. How far do you need it?
If we were looking for a low point, we would have we would have added the X.
If this was flipped over and this was a sag curve, you would have a low point. Obviously, because of the way this is a crest curve, there is no low point. Or if you want to ask, like technically, I guess the beginning and ends would be the lowest points on that parabola. But where's the actual high point? Where does that fall? What is that elevation? On crest curves, that's not necessarily always very important bit of information. However, if you do have a sag curve, that's where engineers are going to design to put like a catch basin in the road. Where's the low point? That's where you would put your storm structure. So low points tend to be a little bit more critical in that aspect.
The high point and low point should be a station. That's
Where does that fall? Where's that station? What's that elevation? So ultimately, what is most important when you're talking about vertical curves are those three equations. Your quadratic, how do you solve for r? And then to find a high point or low point, first you got to solve for the distance, which would be x, and then you can plug that right back in. Any questions? Now, shall we move on to something else? Because we don't have a lot of time. These, I think, will be some of the bigger things to deal with. Possibly, may or may not be, probably.
for this. What do you, I know that they shouldn't be. If you have 100 horizontal distance for every single one of those, wouldn't your equation be the same every single time? Then you keep the same answer.
Well, your distance, your x is always going to change because it's from here to here. From here to here, from here to here, from here to here. No, we're not doing any short chords with verticals. typically when you're dealing with vertical curves, you're going to be looking for elevations. And I will just say, in my whole entire surveying life, from 1996, 1997 to 2025, I never calculated a vertical curve by hand in my life. Profiles always had enough information on them to where I've never had to calculate that. However, just to kind of prep you and get you familiar with, here's how these are, here's how to do them, and you may probably see them in your route surveying class if you advance to that. So I'm also kind of just hoping that when you get to route surveying, if you have to calculate this stuff, you won't be a complete deer in the headlights. You'll have an idea like, oh, yeah. You'll sit back there and be like, don't worry, Jim, I got this. Chris already showed me all this stuff. We're good to go. And he's going to be like, wow, you guys are so good at calculating all this stuff.
Yeah, I know.
That's the way it works in my head right now, anyway.
This was good. Handout, little cheat sheet.
And this is kind of what I think we kind of had worked on before. I would like to look at this bottom cross section really quick. And what I'm really kind of focusing on here, want to focus on, would be looking at slope and various slopes. This thing did not print out all that wonderful, or made a copy of very well. For your typical sections, what may or may not need to be done if you ever have to calculate these by hand is you're going to look at what is the difference, vertical difference, from the center line elevation. So this is kind of a generic thing here. We looked at this a little bit with the intersection details. Or what's the vertical difference between the center line elevation and the back of curb elevation? And we had to apply that vertical difference to actually get to what the top of curb elevation would be. Does that sound familiar? So they give us right off the bat a ½ inch. Oh, it just drives me nuts. So what's a ½ inch converted into decimal feet? Anybody? I don't see calculators moving. Half of an inch is what in decimal feet? No, do it in your calculator. I don't want you to do it off the top of your head. What you got? .5 divided by 12, yeah. So ½ inch, 0.5 divided by 12 to the nearest hundredth would be, yeah, so you could say from the center line, this is 400ths lower than the top of curb. Or I'm sorry, from the center line. The top of curb elevation is going to be 400ths lower than the center line elevation. How about to the face of the sidewalk here? We have a slope of 1 inch per foot, and we know we're going, is that 6 feet?
This is all reference to the center line, right?
Well, that 6 inches would be from your back of curb. 2 here.
Oh, I guess what I'm at.
You see what I'm saying?
Yeah.
So yeah, this 1 inch per foot is here. So if we're going up 1 inch and 6 feet, 6 inches, convert that to decimal feet is
You don't have to like subtract that 0.04 from our 6 inches to relate it back to the center line.
yeah,
Don't.
you do. Yeah, I'm sorry, you do. So here's what I'm looking at here. If I were just to take this and draw this center line and continue this all the way through. Kind of looking like, what is that? So if you were to take 6 inches and convert that to decimal feet is half a foot. However, keep in mind that that half a foot is from the top of curb. So that's not to the center line.
You would add your negative 0.04 back to center line.
So like 46. Because you would just add the 0.04 above the 5.
So let's look at this here. Let's just for simple maths for the fun of it. If I said the center line elevation at this point was 500, we would say our top of curb elevation is 499 point what 96,
Yeah.
and then what would our elevation be here at this point? So if I took that 499.96, that elevation would be 500.46 in that instance. Yeah.
You got 46 there? I got 42.
4.2.
499.96 plus 0.46, right?
No. That 46 hundredths here is from the center line elevation.
Oh,
Half a foot, the 5/10 would be from the top of curb elevation. So even if you just, okay, this is 6 inches here, add 6 inches to your 499.96, what do you get?
Oh, yes. Because you could have also just added that 0.46 to your 500.
Yes.
Because we already.
Yeah. So essentially, yeah, that this is the difference from the center line to that point. Yeah.
It's just a little weird because we solved it first. But like if you were going in order, like down the
If you were
line,
going in order,
I don't think we would have got mixed up.
yeah.
All right.
So I actually had to do this like a long time ago, back when I was your age, like some of my first co-ops, is find out what is the difference in the center from the center line. And then I'd have to find what that center line elevation is, and then do that simple add subtract to find what the elevation would be at that point. From there, we started calculating contours, like to see where, interpolating contours to see where they fell. 1/4 inch per foot and 4 feet. How about that one? What you got?
1 inch. Oh, what do you want? It would be 501.146.
So you're saying 1 inch? Yeah, you're right though. It'd be 1 inch.
But it's not 501.46, right?
No, if you continued on, say that 46, 500.46 plus your 800s.
I had one, and you gotta add one divided by 12.
So the 1 inch you need to put in the decimal.
Yeah.
Where you got it for that 500. Yeah. Here it is.
I would get an actual elevation of which would tell me that that's from the center line, right? 1/4 of an inch per foot, 1/4, 2/4, 3/4, 4/4, 1 inch is 800ths. Add that 800ths to your 500.46 to get you what's the actual elevation here. Yeah?
I got, you add that 800ths to your, oh.
Yeah, because you're
I just,
because you're going up.
I got the wrong number. Nuts. I added 500, I did not add 500.46. So
3/4 of an inch per foot in 1 foot. Am I messing you up?
No, it's just I keep looking from the last elevation and adding that, and I'm like, why would it be on these? Then I realized I got to do 500. That makes sense.
One more thing. Let's do one more thing. You got a 3-to-1 slope. What would your elevation be? Okay, so we hit the right of way and we are at 500.60 elevation. If you were to go out 25 feet at a 3-to-1 slope, what would your elevation be? Up and down. Give me both of them.
25 feet.
For yeah, 25 feet. So at 3-to-1 slope, that's a ratio: 3 feet horizontally, 1 foot vertical. Okay, so it's kind of a run rise, is the way that's looking. So what you would look at there is 1/3 converted to decimal feet. Rise 1 divided by run 3, you get 0.333333333 repeating. That's your slope in decimal form.
Why is the rise the 1 and not the 3?
Because I said so. That's just the way that's written as a ratio.
It's written rise over run.
Right. Correct.
This is run to rise.
The ratio of, if you ever see a slope, which you can see on a set of construction drawings, slopes potentially showing like around detention basins or something, you'll see it's graded at like a 3-to-1 or a 4-to-1 or a 2-to-1. You could run across that in construction drawings. That's just the way that's written, but that is, in all actuality, run over rise, or that's what run to rise, I guess would be more correct to say. Run to rise. So if you take that, your slope is 0.333, infinitely repeating, multiply that by your run, you get a difference in elevation. Your rise would be 8.33. So if you were going up, you would add that 8.33. At 25 feet, I would have 508.93 at 25 feet. Was that
So you added the 26 to the 8, like 9 you're usually leaving, and then add that 500.
Yeah, that would be coming from this elevation. So what is that? 25 feet at that 3-to-1, up, down. The rise is going to be the same. Whether
93.
that's what I got. How about going down? Okay, folks, unfortunately, we're out of time. Didn't really get through everything here, but I think the slope thing was pretty important to look at. We will have some I think I gave you this other packet here to look at, the intersection detail. We looked at that was kind of one of our last labs. So looking at your typical section, what is the back of curb? What's the difference in elevation from your center line to back of curb? Apply that to whatever your center line information is to get the back of curb elevation. I will get this video posted onto Brightspace along with the packet, the final exam. Again, the final exam will be just a paper copy. Please print that out, fill it out, scan it, submit it to Brightspace. You have from when it goes live today to midnight Friday. We do not have anything in person Thursday at lab time, but if you would like to come and hang out and talk surveying and just hang out, we can do that too. I'm good with that. Otherwise, I don't have anything for you. It's been a great semester. I've enjoyed you all. Thanks for coming, and have a good summer semester.